Hey everyone, welcome back, or if you're just joining us, welcome to KSSP Podcast. I'm Spencer.
And I'm Katie. Today we're going to be going over some nebulae, like planetary nebula and supernovas. So let's start with the planetary nebula. So a planetary nebula is a type of emission nebula consisting of an expanding glowing shell of ionized gas ejected from red giant stars late in their lives. So we're going to watch a quick video here going over the different kinds of nebulae.
And it is from NASA Goddard, Hubble's Field Guide to Nebulae. Nebulae, whatever. We'll give it a watch.
The space between stars holds an array of vibrant clouds. Clouds that command our attention. Clouds that create spectacular displays. Clouds that seem familiar, tenuous, and fragile. Clouds that hold clues to star birth and death.
It's very artsy.
NASA's Hubble Space Telescope has
I
imaged
like it.
hundreds of them in extraordinary detail. These vast swirls of gas and dust get their name from the Latin word nebula, meaning cloud or mist. Nebulae is the plural of nebula, and they come in a wide range of shapes, sizes, and forms. Emission nebulae are some of the most spectacular. These opaque, gleaming clouds of gas and dust radiate or emit their own light. Ultraviolet light from nearby stars energizes atoms in the cloud. When the excited atoms lose that energy, they release the light that gives emission nebulae their glow. The Orion Nebula is one of the most famous emission nebulae. Its core, called the trapezium, holds 4 enormous young stars whose ultraviolet light powers the region's intense glow. The Carina Nebula is another vast emission nebula and star-forming region in our galaxy. Within the nebula is a pillar 3 light-years tall, dubbed Mystic Mountain. It cloaks massive young stars, some with jets emerging from the cloud. Hubble's infrared view cuts through the shroud of gas and dust, revealing these radiant jewels. Reflection nebulae shine by the reflected or scattered light of nearby stars. They often have a bluish color because the dust grains in the clouds scatter blue light more efficiently than red light. Not all nebulae shine brightly. Dark or absorption nebulae are inky black clouds of gas and dust that block the light coming from objects behind them. Because they are dark, absorption nebulae are hard to find. We only see them as silhouettes against a much brighter region of space. Most large nebulae are a combination of emission, reflection, and absorption nebulae. Their dark dust lanes may give birth to new stars that provide the light needed to illuminate the cloud. Planetary nebulae are a type of emission nebula powered by a small to medium-sized dying star. As these stars run out of fuel, they periodically blow off their outer layers. The expelled gas expands outward away from the star, forming a bubble or shell around the star. Sometimes, the envelope of debris holds clumps of dense gas that shine like the gems of a necklace. The term planetary nebula is misleading. It comes from late 18th century astronomers who thought their rounded shape looked similar to planets and telescopes of that time. They named them planetary nebulae as a result. Supernova remnants are the diffuse clouds of expanding debris released by a massive star's death explosion. The Cygnus Loop is a vast, expanding, 110 light-year-wide supernova remnant. It is so large that Hubble can only image small sections of it at a time. Some supernova remnants emit their light from a shell of shocked material. Others, like the Crab Nebula, emit most of their light from within the expanding shell. and still other supernova remnants shine as a combination of the two. Nebulae are some of the most resplendent objects in the universe, and thanks to the Hubble Space Telescope, we can study them in all of their magnificent forms.
Pretty.
Yeah, it is so pretty. Space. It's so pretty.
So, yes, it is. This might be a little repetitive, some of it, but I'm going to go over this article too. So nebulae are made up of gas, primarily hydrogen and helium, and fine cosmic dust. These clouds are part of the interstellar medium of extremely low density gas and dust that exists between stars in the void of space. Material so dispersed through the vastness of the cosmos that it can have a density as low as 0.1 atoms per cubic centimeter. In contrast, a cubic centimeter of the air we breathe on Earth would contain about 10 million trillion molecules. So, yes, it's like, what's the opposite of dense? It's the opposite of dense, whatever that word is. I can't think of it.
Light?
I guess, yeah. It's very light. Buoyant, maybe?
Maybe. I don't know, I guess.
I don't know if that applies in space, though, but anyways. Nebulae happen in places where the interstellar medium has become dense enough to form clouds. That could be because gravity has pulled the gas and dust together, or because stars have died and spewed their contents into the cosmos. Several types of nebulae exist, and each individual nebula is a unique showcase of the phenomena and process happening within. They often live side by side with smaller nebulae populating larger clouds of gas and dust to form giant complexes of star birth and death. So, okay, we've got emission nebulae, reflection nebulae, and planetary nebulae. And she also said the absorption nebulae, I think, but that article doesn't go over that one, I guess.
Oh.
So, all right. We've got emission nebulae. They're named because they emit their own light. This type of nebula forms when the intense radiation of stars within or near the nebula energizes the gas. The star's ultraviolet radiation floods the gas with so much energy that it strips electrons from the nebula's hydrogen atoms, a process called ionization. As the energized electrons revert from their higher energy state to a lower energy state by recombining with atoms, they emit energy in the form of light, causing the nebula's gas to glow. Interesting. So the reflection nebulae reflect the light from nearby stars. The stars that illuminate them aren't powerful enough to ionize the nebula's gas, as with emission nebulae, but their light scatters through the gas and dust, causing it to glow, like a flashlight beam shining on mist in the dark. That's a good visual. Planetary nebulae form during the death of low-mass to medium-mass stars. When such stars die, they expel their outer layers into space. These expanding shells of gas form a huge variety of unique shapes, such as rings, hourglasses, rectangles, and more, that show the complexity of stellar death. Astronomers are still studying how these intricate shapes form at the end of a star's life. And as the star casts off its outer layers, it leaves behind its core, which becomes a white dwarf star. And then we've got the next article. So a planetary nebula gallery. A planetary nebula represents a phase of stellar evolution that the sun should experience several billion years from now. When a star like the sun uses up all the hydrogen in its core, it expands into a red giant. In this phase, the star sheds most of its outer layers, even leaving behind a hot core that will soon contract to form a dense white dwarf star. A fast wind emanating from the hot core rams into the ejected atmosphere, pushes it outward, and creates the graceful shell-like filamentary structures seen with optical telescopes. The diffuse X-ray emission seen in about 30% of the planetary nebulas in the new Chandra survey and all members of the gallery is caused by shock waves as the fast wind collides with the ejected atmosphere. The new survey data revealed that optical images of most planetary nebulae with diffuse X-ray emission displays compact shells with sharp rims surrounded by fainter halos. All of these compact shells have observed ages that are less than about 5,000 years, which therefore likely represents the timescale for the strong shock waves to occur. About half of the planetary nebulas in the study show X-ray point sources in the center, and all but one of these point sources show high-energy X-ray that may be caused by a companion star, suggesting that high frequency of central stars responsible for ejecting planetary nebulas have companions. Future studies should help clarify the role of double stars in determining the structure and evolution of planetary nebulas. All right, and then we're moving on to NASA's Webb captures dying stars' final performance in fine detail. Two stars, which are locked in a tight orbit, shape the local landscape. Webb's infrared images feature new details in this complex system. The stars and their layers of light are prominent in the image from Webb's near-infrared camera on the left, while the image from Webb's mid-infrared instrument on the right shows the first time that the second star is surrounded by dust. The brighter star is in an earlier stage of stellar evolution and will probably eject its own planetary nebula in the future. In the meantime, the brighter star influences the nebula's appearance. As the pair continue to orbit one another, they stir the pot of gas and dust, causing asymmetrical patterns. Each shell represents an episode where the fainter star lost some of its mass. The widest shells of gas towards the outer areas of the image were ejected earlier. Those closest to the star are the most recent. Tracing these ejections allows researchers to look into the history of the system. And then we'll see the Hubble captures re-energized planetary nebula. Although the core of the star has stopped burning hydrogen and helium, a thermonuclear runaway at its surface ejects material at high speeds. This ejecta shocks and sweeps up the material of old nebula, producing the filaments and irregular shell around the central star seen in this image, which features data from the Hubble's Wide Field Camera 3 and the Panoramic Survey Telescope and Rapid Response System. And then we have planetary nebula NGC 2440. There's not much to say about this, but it's just really pretty to look at, honestly, and yeah, it just looks like there's a lot of.
Does it say what kind it is, I guess? What type of nebula it is? Or I guess it said planetary, right? Yeah.
I think it is a planet. Yeah, it is a planetary nebula. So there's that one. And then we've got the Hubble's view of planetary nebula reveals complex structure. NGC 6891 is made up of gas that's been ionized by the central white dwarf star, which stripped electrons from the nebula's hydrogen atoms. As the energized electrons revert from their higher energy state to a lower energy state by recombining with the hydrogen nuclei, they emit energy in the form of light, causing the nebula's gas to glow.
Okay. And then we're gonna move on to supernovas. So, have an article here from NASA. What is a supernova? A supernova is the explosion of a star, the largest explosion that takes place in space. And where do supernovas take place? Well, supernovas are often seen in other galaxies and are often difficult to see in our own Milky Way because dust blocks our view. And we may be wondering what causes them. So I guess in that article they mentioned that there were two types, and the first type of supernova happens in binary star systems. Binary stars are two stars that orbit the same point. One of the stars, a carbon-oxygen white dwarf, steals matter from its companion star. Eventually, the white dwarf accumulates too much matter. Having too much matter, it causes the star to explode, resulting in a supernova. The second type of supernova occurs at the end of a single star's lifetime. As the star runs out of nuclear fuel, some of its mass flows into its core. Eventually, the core is so heavy that it cannot withstand its own gravitational force. The core collapses, which results in the giant explosion of a supernova. The Sun is a single star, but it does not have enough mass to become a supernova. And then we're also going to look here. Another article from NASA. Hubble captures three phases of evolving supernova in the early universe. So, in this article, there were 3 different moments in a far-off supernova explosion that were captured in a single snapshot by NASA's Hubble Space Telescope. The star exploded more than 11 billion years ago, when the universe was less than a fifth of its current age of 13.8 billion years. And then with this one, we have a video, and the description for the video is: through a trick of light bending gravity, the Hubble Space Telescope captured 3 different moments in the explosion of a very far off supernova. So we'll watch that short video here too to kind of get a visual. So, and this is by NASA Goddard as well, and Hubble captures 3 phases of evolving supernova.
The Hubble Space Telescope captured 3 separate moments in a far-off supernova explosion in a single snapshot. These moments provide a unique glimpse into the supernova's early life. It is quite rare to detect a supernova explosion at a very early stage, because that stage is so short. It only lasts for hours to a few days, and it can be easily missed. The star exploded more than 11 billion years ago, when the universe was less than 1/5 of its current age of 13.8 billion years. In a single exposure, Hubble captured the supernova's rapid change of color, which indicates temperature change. The early, hotter phase appears blue. As the supernova cooled, its light turned redder. This detection was possible through a phenomenon called gravitational lensing, as first predicted by Einstein's theory of general relativity. In this case, the immense gravity of the galaxy cluster, Abell 370, both bent and magnified the light from the more distant supernova located behind the cluster, like a giant cosmic lens. This lensing effect split and warped the supernova's light, bending it along separate pathways of varying lengths. The different travel times between each path created a time delay that produced 3 distinct images of the explosion at different times that arrived at Earth simultaneously. This is the first detailed look at a supernova at such an early time of the universe's evolution. The research could help scientists learn more about the formation of stars and galaxies in the young universe.
Okay, interesting. It's kind of cool that they were able to capture like the 3.
Yeah.
And then I just have one more article here that is from NASA again, and it is Hubble reveals surviving companion star in aftermath of a supernova. So we'll just read here. NASA's Hubble Space Telescope has uncovered a witness at the scene of the star's explosive death, a companion star previously hidden in the glare of its partner's supernova. The discovery is a first for a particular type of supernova, one in which the star was stripped of its entire outer gas envelope before exploding. The finding provides crucial insight into the binary nature of massive stars, as well as the potential prequel to the ultimate merger of the companion stars that would rattle across the universe as gravitational waves ripples in the fabric of space-time itself. And then there's this image here. It's this artist illustration, shows supernova 22013 GE with its companion star in the lower right. Companion star is impacted by the blast wave from the supernova, but not destroyed. Over time, astronomers observed the ultraviolet UV light of the supernova fading, revealing a nearby second source of UV light that maintained brightness. The theory is that the 2 massive stars evolved together as a binary pair, and that the current survivor siphoned off its partner's outer hydrogen gas shell before it exploded. Eventually, the companion star will also go supernova.
Ooh, interesting.
Yeah, so it's interesting that, like, the star, I guess it makes sense kind of that the star didn't get disintegrated, but it's just interesting that it survived the blast of the supernova, you know? That's just,
Yes.
and it like took in that and like siphoned off it stole the energy from its brother, I guess, if you will.
Yeah, we can call them brothers.
Yeah. And then there's another image in the picture in this article, the evolution scenario for a stripped envelope supernova. So this infographic shows the evolution astronomers propose for supernova 2013 GE, which is the one we just went over. Panels 1 through 3 show what has already occurred, and panels 4 through 6 show what may take place in the future. So the first image, a binary pair of massive stars orbit one another. In the second image, one star ages into its red giant stage, getting a puffy outer envelope of hydrogen that its companion star siphons off with gravity. Astronomers propose this is why Hubble found no trace of hydrogen in the supernova debris. 3. The striped envelope star goes supernova, jostling but not destroying its companion star. After the supernova, the dense core of the former massive star remains either as a neutron star or black hole. 4. Eventually the companion star also ages into a red giant, maintaining its outer envelope, some of which came from its companion. 5. The companion star also undergoes a supernova. And then 6. If the stars were close enough to each other not to be flung from their orbits by the supernova blast wave, the remnant cores will continue to orbit one another and eventually merge, creating gravitational waves in the process.
That's interesting.
Yeah, so that'll be interesting. Like, I don't think we'll probably be around then, but
Well, it's probably happening right now. We're just not capturing
well,
it.
yeah, but we won't
It's
see
so
it.
far away.
Yeah,
We won't see it in our lifetime, though.
unfortunately. I mean, unless we
Let's see
reverse
the
aging or something, But even then, our star might get us then.
Yeah, the sun might get us first.
Yeah. But yeah, so now that we've discussed planetary nebulas and supernovas, join us in the next video where we're going to discuss white dwarfs, neutron stars, and black holes. And as always, you can leave a comment below if you have any ideas for future topics you want us to discuss.
You can find us on Facebook, Instagram, YouTube, Twitter, and TikTok. And we also occasionally do Twitch live streams.
And don't forget to like, follow, or subscribe and turn on notifications so that you know when we do. Otherwise, we'll see everyone in the next video.